By the end of this video, you're going to be flying through these trigonometric integrals, and in about 30 seconds, here's how this video is going to get you there. We're going to start by doing some sine and cosine integrals. So we'll do an integral where cosine has the odd power, one where sine has the odd power, and then we'll do a problem where neither sine nor cosine has an odd power. After we go through that, we're going to go through the tangent secant integrals, and we're going to do all the cases there, where tangent's odd, where secant has an even power, and also where neither of those things happen. And then we'll be talking about cosecant cotangent integrals, which is really just an extension of tangent secant stuff. And then in the last problem, we'll have an integral where we have two trig functions being multiplied together, but they have different angles. So we'll go through all of that, and then I'll give you a problem to try and answer in the comments, and by that point, it should honestly be breezy. Lastly, if you're looking for the notes for this video, I took all my notes from this video and all my other videos on techniques of integration, and I made them into a workbook for you guys. The link to this workbook is going to be right in the description, and now let's get into this video. So starting with our first problem here, we have the integral of sine squared x times cosine cubed of x dx. Now, here's the problem with this integral. We're not going to be able to make some simple u substitution right off the bat. Like, for example, we're not going to be able to just go u is equal to sine of x, and that would make du equal to the derivative of sine of x, which is cosine of x, times dx. Because the issue with making this u substitution is it works great for the sine, right? We get the integral of u squared, but we don't have a cosine of x dx in our integral. We have a cosine cubed of x dx. And so we're going to have to get a little bit crafty here. Now with integrals with sines and cosines to powers, we want to split up whichever trig function has an odd power. And looking at this integral here, that cosine has an odd power. It's cosine cubed. Now real quick, you might be thinking, well, what if sine and cosine both have an odd power? And what if neither of them have an odd power? We'll talk about that a lot more in problem 3. But for now, in problem 1, we see that cosine has that odd power. And that means we're going to split it up. And here's how we're going to do that. We're going to rewrite this integral as the integral of sine squared x times, we're going to take one of these cosines away. And that's actually going to work for our du in our u substitution. So we're going to write this as cosine squared of x times cosine of x dx. So you see now how we've taken that one cosine x away. Now the issue is that if we make our u substitution now and make u equal to sine of x, we still have to deal with this cosine squared of x here. So it'd be nice if we could convert that to a sine. And with a trig identity, we'll actually be able to do that. And the main trig identity that everybody knows is sine squared x plus cosine squared x equals 1. This trig identity is going to be your best friend when you're dealing with sine and cosine integrals. With this trig identity, we're going to be able to convert cosines to sines and sines to cosines. Because, for example here, we're going to be able to convert that cosine because we know that cosine squared is equal to 1 minus sine squared x. Right, just take this identity and subtract sine squared on both sides. So we're just going to substitute that in now to the integral. When we do that, we get the integral of sine squared x times, so now this cosine squared we're writing as 1 minus sine squared x, and then we have that cosine of x dx. So now that we've done that, we can actually go and make our u substitution now. Let's make our u sine of x. Because from all the work that we just did, we set up our du really nice as that cosine of x dx. So du is cosine of x dx. So now let's plug all that in and see how that simplifies our integral. Plugging that in, we get the integral of sine squared. Remember, u is sine now, so that's just going to be a u squared. And that'll be multiplied by a 1 minus u squared. And then cosine of x dx, that is our du. So we'll have a du here. And just multiplying this u squared through, we're going to get the integral of u squared times 1 is u squared, and then u squared times u squared is u to the 4th. So we get u squared minus u to the 4th du. Okay, so now let's go through and integrate here. We can integrate u squared, that's 1/3 u cubed, or we can write that as u cubed over 3 And then we have minus the integral of u to the fourth, that's u to the fifth over 5. And that'll be plus c. So now that we put our plus c in, that should be our answer, right? We're all good. Well, not quite. What is u? U is sine of x. So let's plug that back in. And of course we want to plug that back in because our integral was given with x's, not u's. So our answer should also be given with x's. Remember, u is equal to sine of x. So we're going to write this integral as, instead of u cubed, it'll be sine cubed. That's over 3. Minus, instead of u to the fifth, we'll have sine to the fifth. And that's over 5. And then finally we have plus c. And that is our answer for problem 1. Now look, I know we did a lot of work in this problem. It's probably tough to keep all that straight. So we have another problem that's pretty much just like it, except now which of these trig functions have the odd power? Well, now cosine doesn't have the odd power, sine has the odd power. And that means we're going to be splitting apart a sine here. So we're going to be writing this integral as, I'm going to split off a sine of x. I'll put that over here with the dx. So if I split off a sine of x, I'll be left with a sine squared of x. And then I have cosine to the fourth of x. And I'll write my sine of x dx at the end. Now you can see this integral hasn't changed here. Sine squared times sine is sine cubed. So we recover what we originally had. It's just that now we have all of our u stuff will be right here. We want that all to be cosines. And then our du will be right here with the sine. But of course, like I said, we want all of this stuff to be cosines. And we have a sine squared here. So how do we convert that to cosine? Well, again, we use the trig identity that sine squared plus cosine squared is 1. And now, if we want a substitution for sine squared, we subtract cosine squared on both sides, and we get that sine squared is equal to 1 minus cosine squared. And this is what we're going to be plugging in to our integral. So let's plug that in. We get the integral of sine squared is 1 minus cosine squared. That's going to be times cosine to the fourth. And times sine of x dx. Okay, so now we're all set up to make our u substitution. U is going to equal cosine of x. And du, it's not going to quite be sine of x dx because the derivative of cosine is negative sine. So du is negative sine of x dx. Okay, so let's see how this cleans up the integral. We get the integral of 1 minus cosine is u, so this will be a u squared. And then cosine to the fourth, that'll be a u to the fourth. And then lastly, we have a sine of x dx, but our du is negative sine, so that means if we divide a negative 1 on both sides, we get that negative du is equal to sine of x dx. So substituting for that sine of x dx, we write negative du. Okay, so now let's clean some things up here before we integrate. First off, we can multiply that u to the fourth through. And if you really want to be clever about this, when you substitute in that negative for the du, what you can do is instead of putting that negative on the du, put that negative on the u to the fourth, and then multiply that negative u to the fourth through to the 1 and the negative u squared. So I'll transfer that negative right over here. Okay, now that helps you see a little bit better what you're about to do. That negative u fourth multiplies to the 1, giving us negative u to the fourth. And it will multiply to the negative u squared, giving us a positive u to the sixth. And so you can write that as negative u to the fourth plus u to the sixth du. Or, to be honest, if you want to write it a little bit nicer, you can do u to the sixth minus u to the fourth du. That's really up to you. It's honestly a personal preference. But now let's go and integrate. And the integral of u to the sixth is what? Well, that'll be 1/7 times u to the seventh. And so we can write that as u to the seventh over 7. Now next, what about the integral of u to the fourth? Well, that'll be 1/5 u to the fifth, or you can write it as u to the fifth over 5. And then we have plus c. Now, we are not 100% done yet, right? Because what's the one thing we have to do before we're done with the problem? Well, we have to substitute in that u is equal to cosine of x. And doing that, we're going to get, instead of u to the 7th, cosine to the 7th. That'll be over 7, minus, instead of u to the 5th, cosine to the 5th. That's over 5. And then we have plus c. And that is our answer for problem 2. Okay, so now that that's taken care of, we're going to move on to an example where now neither of the trig functions have a odd power. So we need to talk about that case. And also another case that we haven't talked about is where both trig functions have an odd power. So what happens if we have something like sine cubed of x times cosine cubed of x? Well, for an integral where we have both of the trig functions having an odd power, you can just break up whichever one you want to. It really doesn't matter. So for example, let's say here that we want to break up the cosine. And we write this integral like the integral of sine cubed of x times, we split off one of the cosines, so we'd be left with a cosine squared. And then the cosine that we split off goes next. And then what we can do from there, since this is our du, that means our u is going to be sine. And that means we want the rest of this integral to be sine, so it gets covered in the u substitution. And that means that cosine squared needs to get converted to a 1 minus sine squared using that trig identity. So that's how you would handle an example where both sine and cosine have odd powers. And we're going to go through a full example of that in the extended video that I have where we go through 18 more trig integrals. And it's not just more problems, they also get harder in difficulty as well. So that extended video is linked in the description. But as far as the other case, the last case that we haven't covered yet, where sine and cosine both have even powers, now we can't use that technique that we've been using in problems 1 and 2. Now we have to use a different trig identity. The trig identities we need to use here are the half angle identities. That sine squared is 1 minus cosine of 2x over 2. And cosine squared is 1 plus cosine of 2x over 2. And how I remember these two identities is that they both look almost identical, they just have a difference of a sign. One has a minus, one has a plus. And how I remember which is I go, well, cosine and cosine match, so it's positive. And sine and cosine don't match, so it's a negative. So those are the two identities that we're going to be using here. So let's plug those in to our integral. And when we do that, we get the integral from 0 to pi over 2 of sine squared of x we can write as 1 minus cosine of 2x over 2. And cosine squared of x we can write as 1 plus cosine of 2x over 2. Now, there's a few things that we can do here to simplify, but the first and foremost, like what I want to do is, I see we have two 2's in our denominator, and 2 times 2, that's 4. So what I'm going to do is I'm going to pull out a 1/4. And that'll take care of these two 2's. I've pulled them out of the integral. So now what I'm left with is 1 minus cosine of 2x times 1 plus cosine of 2x dx. So now let's multiply these out. We have 1/4 times the integral from 0 to pi over 2 of 1 times 1, which is 1, 1 times cosine of 2x, which is a plus cosine of 2x. We have negative cosine of 2x times 1, that's negative cosine of 2x. And then lastly, we have a negative cosine of 2x times cosine of 2x. That's going to be a negative cosine squared of 2x dx. Okay, so I've written everything out now. Now you can see that the two middle terms cancel, And we actually should have been able to tell that those were going to happen already, that the middle terms were going to cancel off. Because look at what we have being multiplied here. These two binomials are conjugates, and that means that the cross terms are going to cancel. And so all you actually have to worry about when you multiply these two is the 1 times 1 and the two last terms being multiplied together, the negative cosine of 2x and the positive cosine of 2x. But that's of course only when you have conjugates. You're not going to get conjugates every single time. All right. So now we get 1/4 the integral from 0 to pi over 2 of 1 minus cosine squared of 2x dx. Now what we can do is we can use the half angle identity again on this trig function. And we can write this cosine squared of 2x as 1 plus cosine of, we have to double that angle again, so we make it 4x this time, and we put it over 2. And the reason why we need to do that is because we can't integrate a cosine squared. So we're forced to use the half angle identity once more, and the only place where people really get tripped up here is that they forget to double this angle again. Right? Whenever you use the half angle identity, that angle that I have highlighted here has to get doubled. So just make sure you put a 4x there. But yeah, we're all good to go here. Let's simplify this a little bit. All right, this is 1/4 the integral of 0 to pi over 2 of, this will be a 1. Splitting this fraction up here, I have a negative 1/2. And then I have a negative cosine of 4x over 2. Okay, and now I have a 1 minus a half, which I know is a half. So I get 1/2 minus a cosine of 4x over 2 dx. And if you really want to here, what you can do is you can see that both of these denominators have a 2 in it. You can yank that 2 out. You can factor out that 1/2, put it outside of the integral, and you have a 1/2 times a 1/4 outside of the integral, which is a 1/8. That's if you really want to. You could just integrate like this. So our final integral before we start integrating is going to be 1/8 times the integral from 0 to pi over 2 of, if I get rid of these 2's in the denominator here, this is just a 1 minus cosine of 4x. Okay, so now I can integrate. And doing that integration step, the integral of 1, that's x. And then I have the integral of cosine of 4x. Now, you could use a u substitution for that. I wouldn't go through and do that because it's a lot of work that you just don't want to have to show, especially on a test, because tests are timed, right? So here's how I would think about that in my head. If we were taking a derivative of cosine of 4x, well, that would be negative 4 times sine of 4x. Right? Why is that? Because, well, the derivative of cosine is negative sine, and you leave the inside alone. And chain rule states that you have to multiply by the derivative of the inside. So the derivative of 4x, that's 4, and that's where this 4 comes from. So with that in mind, let's now talk about the integral of cosine of 4x. And yes, you could do that with a u substitution, but you could also think about it as the reverse of chain rule, because that's what a u substitution is, where u substitutions are reversing chain rule. So what we can do is we can take the integral of this and leave the inside alone. So the integral of cosine is sine. So we write sine of 4x. And then instead of multiplying by the derivative of the inside, divide by the derivative of the inside. The derivative of 4x is 4, so we write sine of 4x over 4. And that's how you can do an integral like this very quick and right in your head. So we get sine of 4x over 4 for this integral. Okay, and that's going to be evaluated from 0 to pi over 2. So let's do this evaluation step now. And first, we're going to plug in pi over 2 for x. When we do that, here we get pi over 2 minus sine of 4 times pi over 2. What is 4 times pi over 2? 4 times pi over 2 will be 2 pi. And that'll be over 4. Then you have minus, plug in 0. We get 0 minus a sine of 4 times 0, which is just 0. And that's over 4. Okay. So continuing on here, we see a lot of things go away here because we have a sine of 2 pi. We know that's 0. So this term goes to 0. This is already a 0. And then you have sine of 0, which again is 0. So the only thing we have left is this pi over 2 here. So our final answer is 1/8 times pi over 2, which is pi over 16. And there we go. We have our answer to problem 3. So moving on to problem 4, we have the integral of tangent to the 6th times secant to the 4th dx. So now instead of dealing with sines and cosines, we have tangents and secants. So how do we do an integral like this? Do you go and get the workbook that has all my notes for all of my videos on techniques of integration? Well, you could do that, but for tangents and secants here, we need a rule. Like we had a rule for sines and cosines, and I think it'll be good to go over the whole rule for sines and cosines because then you'll see how it extends to secant and tangent. So remember that what we were trying to do with our sine cosine integrals was we wanted to see which of these trig functions had an odd power. Okay? If neither of them had an odd power, if they both had even powers, then we would use those half angle identities. But let's say that one of them were odd. Well, if sine had the odd power on it, then what we would do is make our u the other trig function. We'd make our u cosine. And that means our du would be a negative sine of x. So in our trig integral, we'd want to separate out a sine. So you can see that in, was it problem 2, right? Yeah, problem 2, we had sine had an odd power, so we had to split apart that sine to give us that sine of x dx. And that was how the du got covered. But for cosine having the odd power, now our u, again, it's the other trig function, it's going to be sine. And our du, that's the derivative of sine, that's cosine. So we had to split apart the cosine to where one of the cosines got covered with the du, and the rest of the cosines we converted to sines. Now let's say that both sine and cosine had odd powers, well then you could do either or. You could either make your u cosine x, or you could make your u sine of x. But that was the rule for sines and cosines. Now what is the rule for tangents and secants? Well, it's kind of the same idea. Except, with tangents, yes, we want the power to be odd, but with secants, we want the power to be even. And you'll see why that is when we go and do these integrals. But for tangent, if tangent has an odd power, then what you're going to do is you're going to make your u, again, the other trig function. So u would be secant. And your du, that's the derivative of secant, that'll be secant tangent. And so what you'll need to do is take out a secant x tangent x dx from your integral, and that will be your du, and the rest of the stuff you need to convert to secants. Now what about if the power on secant is even? Well, then your u, again, the u is always the other trig function, that'll be tangent. And your du, that's the derivative of tangent, which is secant squared. And so what you'll want to do is separate off a secant squared to get covered with the du, and the rest of the secants you'll convert to tangents. Okay, so that's generally the rule for tangents and secants. If both of these things happen, if tangent is odd and secant has an even power, then you can do either or. And if tangent is even and secant is odd, so neither of these things work, then it gets a little bit messy and you might have to convert to sines and cosines or use a trig identity or just figure something out. I'll give you a problem where we do that. That'll be problem 6. But yeah, that's the rule for tangents and secants. And this also extends to cotangents and cosecants. So cotangent, we want to be odd, and cosecant, we want to be even. And we'll do some integrals of that as well. So I get what you're probably thinking at this point. You might be like, well, how am I supposed to remember all this? How am I supposed to remember what trig function needs to have an odd power and what trig function needs to have an even power? Well, here's how I remember all this. The big 3 trig functions, sine, cosine, and tangent, we're looking for those to have odd powers. All of them. And secant, the one that goes with tangent in these integrals, we want that to have an even power. And you can remember that it's even because it's not in this big 3. And then, what are the other trig functions? Well, cotangent and cosecant. And then you just got to remember that cotangent goes with tangent. That's easy to remember because that's also a tangent. And then cosecant will go with secant. So that's all the rules for trig integrals in a nutshell. And so let's use that for this problem here, for problem 4. Now remember, with these trig integrals, with tangent and secant, we want tangent to be odd or secant to be even in power. And do we have either of those things happening here? Well, tangent's not odd. It's got a 6 in the power, but secant has a 4 in the power that is even. So if secant has an even power, then our u will be the other trig function, that's tangent. So that'll be what we use for our u substitution. And then our du, well, that's the derivative of tangent, which is secant squared. So what we need to do to make this u substitution is free up a secant squared of x dx in this integral and convert everything else to tangents. Okay, so we can do that by splitting up the secant. We have a secant to the 4th here, and we can write that as secant squared times another secant squared. Now we've got this secant squared of x dx getting covered by the du, and then this other secant squared, we've got to convert that to tangents. And how do we do that? Well, there's another trig identity that you need to know for that, but you don't need to memorize it. If you start with sine squared plus cosine squared equals 1, I'm not going to write the x's here. If you take this regular trig identity and you divide by cosine squared on each side, what you end up getting is your identity for tangents and secants that you need. Sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And then 1 divided by cosine squared is secant squared. And right there, you get your identity for tangents and secants. And we'll do this later, but if you divide each side by sine squared instead of cosine squared, you'll get the cotangent cosecant identity. So tangent squared plus 1 equals secant squared is the identity that we're going to use here. And we can just plug that in for the secant squared here. We're going to make that a tangent squared plus 1. So we get the integral of tangent to the 6th of x times secant squared we're writing as tangent squared plus 1. And then we have a secant squared of x dx. And it looks like I need to make myself a little bit of room here. Okay, so now we're all good to actually go and make this u substitution. Everywhere we see a tangent of x, we're going to make that a u. So this integral becomes, instead of tangent to the 6th, u to the 6th. And then that'll be multiplied by a u squared plus 1. And that's going to be multiplied by secant squared of x dx, which is du. Now the last thing that we need to do before we can integrate is distribute that u to the 6th through. U to the 6th times u squared is u to the 8th, and u to the 6th times 1 is u to the 6th. So now let's integrate. The integral of u to the 8th is going to be u to the 9th over 9. And the integral of u to the 6th will be u to the 7th over 7. And that will be plus c. But of course, that's not our final answer here. We need to plug in what u is. And remember, u is tangent of x. So plugging that back in, we get tangent to the 9th of x over 9 plus tangent to the 7th of x over 7 plus c. And that's the answer for problem 4. Now moving on to problem 5, again remember what we're trying to get for tangents and secants. Tangent, that's part of the big 3. We want that to have an odd power. And then secant, that's not a part of the big three, we want that to have an even power. So is either of those things happening here? Well, tangent does have an odd power. And so what that means is that secant, the other trig function, is going to be our u. So our u substitution will be that u equals secant of x, and du will be secant tangent. That's the derivative of secant. So now what we need to do is we need to get a secant x tangent x dx separated out in this integral. So let's take one tangent away and one secant away. So we'll rewrite this integral as tangent to the fourth of x times secant to the sixth of x. And then those two trig functions that we just plucked, we're going to put those here. So we have one secant and one tangent dx. Okay, so what do we do now? Well, we can see that this secant tangent will completely get covered by the du, right? That's why we put it there. And this secant to the sixth, that'll get covered with our u substitution. But this tangent to the fourth will not. And so we need to convert it to secants. So if we want to convert this to secants, of course, this isn't a tangent squared. This is a tangent to the fourth. So how do we do that with our identity? What we can do is write this in terms of tangent squared. We can write it as tangent squared squared. That's tangent to the fourth. And then we copy everything else over. So now that we've gone and done that, we can plug in for our tangent squared using our identity. And remember that identity is tangent squared plus 1 equals secant squared. If we want to plug in for tangent squared, we just need to subtract 1 on both sides of this identity. And we're going to get that tangent squared is secant squared minus 1. So let's plug in. We get the integral of secant squared minus 1 squared times secant to the sixth of x times secant x tangent x dx. And now that we've gone and done that, let's use our u substitution, which I put all the way down here. U is secant x, so this will be a u squared minus 1 squared. Secant to the sixth is a u to the sixth. And then secant x tangent x dx is a du. Awesome. So now that we've done that, let's try to simplify this before we integrate. U squared minus 1 squared, you can multiply that out. Take as much time as you need. That's going to be a u to the fourth minus 2u squared plus 1. And then we have a u to the sixth du. So now, just multiply that u to the sixth through. We'll get u to the 10th minus 2u to the 8th plus u to the 6th du. Okay, so now we're ready to integrate. Integrating this, we get the integral of u to the 10th, which is u to the 11th over 11. Then we have minus 2 times the integral of u to the 8th, which is u to the 9th over 9. And then we have the integral of u to the 6th, which is u to the 7th over 7. Then we have plus c. And so now the only other thing we have to do before we get our answer is plug back in what u was. U is secant of x. So plugging that in everywhere we see a u, we get secant to the 11th of x divided by 11 minus 2 times secant to the 9th over 9 plus secant to the 7th over 7 plus c. And that is our answer for problem 5. All right. So moving on to problem 6. This problem is pretty nasty. This might be the nastiest problem that we go over in this video. Because remember what we want to have happen with these tangent secant integrals. We want tangent to have a odd power and we want secant to have an even power. Are either of those things happening here? Well, tangent has an even power, that's too bad, and secant, that's to the first power, that's an odd power. So neither of the things we want to happen are happening here. And that means we have to get a little bit clever. So what you can do from here, and what will work a lot of the time, is converting the sines and cosines, okay, and trying to make this into a sine cosine integral, or maybe there'll be another way that you can figure out to do it. But here, you can try converting to sines and cosines here. You'll eventually end up back with tangents and secants. It's a pretty nasty integral. So here's how we're going to go through and solve this one. What I'm going to do is use a trig identity. I'm going to substitute in for tangent squared. And remember from the last problem that tangent squared is the same thing as secant squared of x minus 1. And then I have times secant x dx. Okay, so now I'm going to multiply that secant through. So I get secant cubed of x minus secant of x dx. Okay, so now we've got two integrals to deal with here. We've got the integral of secant of x, and then we have the integral of secant x. So we can write this out, if you want, like this. Now, the integral of secant of x, that's just an integral that honestly you should memorize. I hate memorizing it. It's not a fun integral. The integral will, I'll tell you what the integral is in a little bit, but actually going and finding this integral, I can make another video on that. That's a whole nother process that really you'll only have to do once and then you just remember it from there. But the integral of secant cubed, this also pops up a lot when doing these trig integrals. We've got to find some way of doing that. And the way that you can integrate secant cubed is with integration by parts. Because you can think of this as the integral of secant of x times secant squared of x dx. And if you write your integral like that, then you can see we have two things being multiplied together, and we do know the integral of secant squared of x dx. So that can be our dv, and then our secant will be our u. So our u, like we said, is going to be secant of x. Our dv is secant squared of x dx. And then from there, we need to integrate to find our v, and we need to take the derivative to find du. Now, du, that's the derivative of secant of x, that's secant tangent, times dx. And of course, I ran out of room. Might as well color code this while I'm at it. And then the integral of secant squared, that's tangent of x. So this is what we'll use for integration by parts for this integral. And then we'll have to tack on that integral of secant of x. So we get that this integral right here is equal to u times v, which is secant of x times tangent of x, minus the integral of v du, which is tangent of x times secant of x tangent x dx. And if I multiply those two, I can write this integral as tangent squared times secant of x dx. And then we have, after we do all that integration by parts, we got this integral of negative secant x. So now that we're here, remember what this is equal to. The integral that we started with was the integral of tangent squared secant x dx. And that is exactly the integral that we ended up with right here. And so we can do that weird integration by parts trick where we add the integral to the other side. So this is going to look pretty messy, but I'll try to fit this all on the screen here. So I'll need to make a quick cut. This monstrosity is what we actually have going on here. And again, we're going to add that integral to the other side. So we add the integral of tangent squared secant on both sides. And once we do that, this goes away. And we're left with 2 times the integral of tangent squared times secant x dx is equal to secant tangent minus the integral of secant of x. And so now we can divide by 2 on both sides. And that will give us that the integral of tangent squared of x, secant of x dx, is equal to secant tangent minus, I'll write out what the integral of secant is now, so we don't have to do another line. The integral of secant is the natural log of secant x plus tangent x. And it looks like I need more room. And this is all over 2. And of course, we can't forget our plus c. Whew, awesome. I'm glad that problem's over. So now that we finished that monster of a problem, let's move on to problem 7. And honestly, these last 2 problems we're going to make pretty light work of. But before we get into that problem, I think I sense a presence. Oh, look at that. It's actually just my workbook that has all of my notes for all of my videos on techniques of integration. How crazy and self-serving. So anyways, getting into this problem here, this is a cosecant cotangent integral, and this is very similar to a tangent secant one. For a tangent secant integral, we know that we want tangent to have an odd power, right? And we want secant to have an even power. And we can remember that because sine and cosine, once you have odd powers, and tangent goes with sine and cosine, right? That's the big 3. And then secant is not in the big 3, and so that has an even power. But how does that work for cotangent and cosecant? Well, tangent, replace that with cotangent. And secant, replace that with cosecant. And now we see that we want cotangent to have an odd power, or cosecant to have an even power. And are either of those things happening here? Well, cotangent needs to have an odd power. It doesn't here. And cosecant, we want to have an even power. It does here. And so what does that mean for us? Well, that means that our u substitution is going to be for the other trig function. It's going to be for cotangent. So we're going to get u equal to cotangent of x. And then du is going to equal what? What's the derivative of cotangent? You might not have the derivative of cotangent memorized right off the top of your head because the derivatives of cotangent and cosecant really don't come up all that often. And, well, if you don't know those derivatives off the top of your head, fear not. It's literally just like the derivatives of tangent and secant. Here's how similar they are. The derivative of tangent is secant squared. And the derivative of cotangent is very similar. It's cosecant squared, but you just have to make it negative. And the same kind of pattern works for the relationship between secant and cosecant. The derivative of secant is secant tangent, and the derivative of cosecant is cosecant cotangent, except again, we make it negative. So you see how those are kind of like mirrors of each other? So yeah, the derivative of cotangent, just think about the derivative of tangent. The derivative of tangent is secant squared, so the derivative of cotangent will be cosecant squared, except we know we have to make it negative. And then we're going to have a dx there. So now that we have our du, let's split out a cosecant squared in this integral. So we're going to get the integral from pi over 4 to pi over 2 of, I'll write the cotangent first. So we have cotangent to the 4th of x times, I'll split out a cosecant squared from here, leaving me with a cosecant squared. And then here's the other cosecant squared. And I have dx. And we're all good, right? These still multiply to be cosecant to the 4th. And now that gives us our du with the exception of that negative. So what we can do is divide by -1 on both sides and get the actual substitution that we're going to use, that negative du is equal to a positive cosecant squared of x dx. Okay, so all that is good. So we know our substitution for du, and all of these cotangents get taken care of with our u substitution. But then we have this cosecant squared left over, and we have to convert that to cotangents so it gets covered in the u sub. And how we can do that is using the Pythagorean identity for cotangents and cosecants. And you don't have to memorize that. That starts from sine squared plus cosine squared equals 1. Okay, you can find it using that. What we can do from this identity is we're not going to divide by cosine squared on both sides, because as you can see here, that would give us a tangent squared. That's how we find the tangent secant identity. What we're going to do is divide by sine squared on both sides, because as you can see, when we divide by sine squared on both sides, that's going to give us a cotangent squared and a cosecant squared. That's exactly what we want. So we get 1, that's sine squared over sine squared, plus cosine squared over sine squared, that's cotangent squared, is equal to 1 over sine squared, that is cosecant squared. So this is the identity that you need to know for cotangents and cosecants. And remember, what we're trying to plug in for here is cosecant squared. And this identity tells us that cosecant squared is 1 plus cotangent squared. So that's what we'll be plugging in. So we're going to write this integral as the integral from pi over 4 to pi over 2 of cotangent to the 4th of x times, we just said that cosecant squared was 1 plus cotangent squared. And that's times cosecant squared of x dx. And now it seems like we're all good to substitute, right, and do our u substitution. Well, not quite. There is one more thing that you have to worry about here. This is a definite integral, and that means we need to worry about the bounds when we do our u substitution. You don't want to get all the way down to the end of the problem, and trust me, I've done this a million times, and forget to change your bounds, because then you got to go all the way back up through your work, change all those bounds, and it's just a mess. Done that a million times. I hate it. So what we want to do here is find the corresponding u values for when x equals pi over 4, that's our lower bound, and when x equals pi over 2, our upper bound. And how do we do that? We'll just plug into our u substitution. U equals cotangent of x, and what happens when x is pi over 4? Well, then we're looking for cotangent of pi over 4, and cotangent of pi over 4 is the same thing as 1 over tangent of pi over 4. And tangent of pi over 4, that's the same thing as tangent of 45, that's 1. So we get 1 over 1, and that gives us 1. So when x is equal to pi over 4, u is equal to 1. Now, what about our other bound, pi over 2? We'll plug pi over 2 in for x into our u substitution, and what you get is 1 over tangent of pi over 2. But you might be a little confused by that because tangent of pi over 2 is undefined, or tangent of 90 is undefined. So what you can do is you can write this as cosine of pi over 2 over sine of pi over 2. Right, that's what cotangent is. If tangent is sine over cosine, then cotangent's cosine over sine. And cosine of pi over 2 is just 0. Sine of pi over 2 is 1. So you get that when x is equal to pi over 2, u is equal to 0. So the bounds for our integral are not going to be 0 to 1, because remember what the order of things are here. When x is equal to pi over 4, u is equal to 1. So our lower bound's actually going to be 1, and then our upper bound will be the 0. And then let's make our u sub here. Cotangent to the 4th will become a u to the 4th. 1 plus cotangent squared is going to be a 1 plus u squared. And then cosecant squared dx is a negative du. So we're going to put our du here, and I'll put the negative on the outside of the integral. Now, what the negative can do outside of the integral is it can switch the bounds of the integral. So what I'll do is I'll rewrite this as the integral from 0 to 1 right? And now it'll be a positive integral now. That's the negative got used up when it changed the bounds. And I'll multiply the u to the fourth through here, and that'll give me a u to the fourth plus u to the sixth du. So now let's go through and integrate. And integrating, we're going to get the integral of u to the fourth is u to the fifth over 5. And the integral of u to the sixth is u to the seventh over 7. And we need to evaluate that from 0 to 1. Now, you can already see that the zeros, right, that's just going to give us a 0 everywhere. So really all we have to care about is plugging in the 1. And so if you just want to go right away and see that this is 1/5 plus 1/7, feel free. If you're a little confused by that and you want me to, just show this out, then okay, let's do that. First, let's plug in the 1. That'll give me a 1 to the 5th power over 5 plus 1 to the 7th power over 7. And then I need to plug in 0. And like I was just saying, that 0 is going to get rid of everything, because you're going to get a 0 to the 5th power over 5 plus a 0 to the 7th power over 7. And we know that 1 to the 5th power is 1, and 1 to the 7th power is 1. So this entire thing simplifies to 1/5 plus 1/7. Where this entire second piece goes to 0, because you get a 0 over 5 plus 0 over 7. Now you can find common denominators between 5 and 7. That's going to be 35. So if we get our common denominators here, multiply this guy by 7 over 7 to get 7 over 35. And multiply 1 over 7 by 5 over 5 to get 5 over 35. And finally, 7 plus 5, that's 12, so we get 12 over 35. And that is our answer for our second to last problem for this video. Okay, so that was problem 7. Problem 8 is quicker, I promise. Problem 8 is something different that we haven't dealt with yet, and that's when you have two trig functions being multiplied together. Really, you only deal with sines and cosines with this. And some calc classes don't even go over these types of integrals, so this might not even apply to you. But you can see a couple different cases here. You can see two sines being multiplied together with different angles. You can see two cosines being multiplied together with different angles. And you can see a sine and a cosine being multiplied together with different angles. And all of these have their own identities. So what's the identity when we have two sines being multiplied together with different angles? Great question. I should probably go figure that out. So this is the trig identity that you need to use in this problem. The other two cases have their own two trig identities, and those examples I go over in the extended video. But as far as the trig identity for this problem, we have sine of a times sine of b equals cosine of a minus b minus cosine of a plus b all over 2. And okay, so what are a and b going to be here? Well, you could make a 2x and b 6x, but then if I did a minus b, that would give me a negative under, as the argument of the cosine, and I would rather not have that. So I'm going to make a 6x and b 2x. And that way I'll get a 4x in that first cosine, which will be nice. So I can change this integral with that trig identity to be the integral of cosine of 6x minus 2x minus cosine of 6x plus 2x all over 2 dx. And the integral sign kind of looks a little wimpy. I think we should make that a little bigger. There we go. Okay, let's simplify this down. This will be the integral of cosine of 4x minus cosine of 8x all over 2. And actually what you could do is, if you don't need to write it that way with the 2 still in the integral, you could just bring that over 2 outside of the integral as a 1/2. Then you just have cosine of 4x minus cosine of 8x dx. So now let's go through and integrate this. Now you can do these integrals with u substitutions, but it's going to be way quicker and I think easier too if you do this in your head. So remember that u substitutions are reverse chain rule. So how do we reverse chain rule for cosine of 4x? Well, what is the integral of cosine? the integral of cosine sine, and just leave the inside alone. And then what is the derivative of the inside of the 4x? The derivative of 4x is 4, and with chain rule we would multiply that out front. But when we integrate, we're going to divide the derivative of the inside. So we divide by 4. Then we have minus, what's the integral of cosine of 8x? Well, what's the integral of cosine? The integral of cosine sine, and again, leave the inside alone. And then divide by the derivative of the inside. The derivative of 8x is 8, so that is the thing we divide by. And then we have our plus c at the end. So now all that's left to do is multiply that 1/2 through. So we're going to get sine of 4x over 8 minus sine of 8x over, this will be 8 times 2, which is 16. And then we have plus c. And that is the answer for the last problem for this video. So that is trigonometric integrals in a nutshell, and if you feel pretty comfortable with this now, then here's a problem for you to try and answer in the comments. Here we have the integral of sine to the 5th of 2x times cosine to the 3rd of 2x dx. I know this 2x might be a little bit scary, but these are the same angle, so it's not going to solve like problem 8 where we have to use some kind of identity like that. It's going to solve like problems 1 or 2. Just keep that 2x the same all the way down, and then when you integrate, you'll have to deal with the 2x on the inside finally. So give that problem a shot. Let me know what your answer is in the comments. And if you have any questions on anything we talked about in this video, again, let me know in the comments and I'll try to get back to you when I can. Now remember, I do have that extra video where you and I will go through and solve 18 more trigonometric integrals. We'll be doing some more practice with integrals like this, and we'll be getting into some harder problems, some messier problems, all that stuff. So especially if you have a quiz or a test coming up on this kind of stuff, I highly recommend you check out the link to that extra video in the description. Lastly, make sure that you're subscribed to this channel. Listen, this video took me forever to make, so I better be getting some pity subscribers out of this. But yeah, anyways, that's going to do for this video, and I'll see you soon.